So let's take a look at partial derivatives. So what is the limit definition of a partial derivative? Well, remember in regular derivatives when we had f of x, and let's say we're trying to find f prime of x, the limit definition for the derivative was the limit as h approaches 0 of f of x plus h minus f of x over h. And so now, given a multivariable function, f of x comma y, when we take the partial derivative, so the partial derivative can be written in several ways. It can either be written as f sub x of x comma y. It can also be written as the partial derivative of f with respect to x. And it can also be written as the partial derivative of the function f of x comma y with respect to x. And so I'm just going to go with the first notation here. F sub x of x and y is going to equal, the limit definition is going to be the limit as h approaches 0 of f of x plus h comma y minus f of x comma y over h. So notice there are several similarities and some differences between the standard derivative limit and the partial derivative limit. And so if you can take the partial derivative of f with respect to x, you can also take the partial derivative of f with respect to y as well. So we have f sub y of x comma y. And so the limit definition is just going to be a little bit different. So the limit as h approaches 0 of f of x comma y plus h. So this time the h goes along with the y, minus f of x comma y over h. And so the main takeaway from this is when we derive with respect to x, or when we take the partial derivative with respect to x, we're going to treat x as the variable, so we derive x, but then y is going to be treated as a constant. And so the opposite happens when we derive or take the partial derivative with respect to y. When we do that, then x is going to be treated as a constant, and then y is going to be the variable which we differentiate. So for these next set of problems, let's go ahead and find the first partial derivatives of the function. Now what does that mean? Once again, we're going to find the partial derivative of f with respect to x, and also we're going to find the partial derivative with respect to y. So first let's go ahead and find the derivative or the partial derivative of f with respect to x. So it can be written as f sub x. And so remember, when we derive with respect to x, we're going to treat the x as a variable, and then the other variable is y, so we're going to treat y as a constant. So since 3x is a variable, let's go ahead and take the derivative of 3x. Obviously that's just going to be 3. And then we have a negative 2y to the fourth. Now remember, 2y to the fourth is a constant, and the derivative of a constant is always going to be 0. So 3 minus 0 will give us 3. And so that is going to be the partial derivative of f with respect to x. So now let's find the partial derivative of f with respect to y. So f sub y. So now x is going to be the constant, and negative 2y to the fourth is going to be the actual variable that we derive. So the derivative of a constant is obviously 0. And then we have the derivative of negative 2y to the fourth. We just use the power rule, is negative 8y cubed. So we get negative 8y cubed as the final answer. So for number 2, we have z equals x times e raised to the power of 3y. So notice it's not in the form of x or f of x comma y. Instead it's in the form of z equals. So we cannot use a notation where we have f sub x or f sub y. Instead we have to use a standard notation where we're going to take the partial derivative of the function to the partial derivative of z with respect to x. And the next one we'll do is with respect to y. So once again, we're deriving with respect to x. So x is going to be the variable of differentiation, and y is going to be treated as a constant. So e to the 3y, the entire thing is a constant. So if we have a constant multiplied by x, the derivative is just simply the constant. So the derivative of z, or the partial derivative of z with respect to x, is simply just e to the 3y. So now let's find the partial derivative of z with respect to y. So in this case, y is going to be, well, we differentiate, and x is going to be a constant. So remember, the derivative of e raised to some function u, so the derivative of e to the u is going to be equal to e to the u times u prime. So if x is going to be a constant, then the derivative of z with respect to y is going to be x times e to the u, so e to the 3y, multiplied by the derivative of the inside function, So the derivative of 3y is simply just 3. So we get 3x e to the 3y as the derivative with respect to y. So now for number 3, we have f of xy equals x minus y over x plus y. So let's go ahead and first find the partial derivative of f with respect to x. So f sub x. So now that is going to equal, well, notice since x is the variable that we derive, it is both on the numerator and the denominator, and so we must use the quotient rule. So once again, in the quotient rule, if you have some function on the top u, another function on the bottom v, and you're trying to take the derivative of u over v, then the formula is going to be the low, so v times the derivative of high, minus high times the derivative of low, all over low squared. So in order to derive, we're going to take first the lower function here, x plus y, and multiply it by the derivative of the top function. So if x is the variable that we derive, the derivative of x is 1, and y is a constant, and so the derivative of a constant is 0. So it's simply just going to be 1 minus 0 or 1. Now minus the higher or the top function is just x minus y times the derivative of the lower function. So the derivative of x plus y, now derivative of x is simply 1, and the derivative of y is 0, because y is treated as a constant, so 1 plus 0 is 1, and then all over the lower function squared, so x plus y squared. So when I simplify, we'll get x plus y minus x plus y if we distribute the negative over x plus y squared. So notice the x's will cancel. So y plus y is 2y, so we'll get 2y over x plus y squared as the first partial derivative of f with respect to x. So now let's derive f, or take the partial derivative of f with respect to y. So in this case, y is going to be the variable that we derive and x is going to be treated as a constant. So we're still going to use the quotient rule. So we take the bottom function first, so x plus y. So low times the derivative of the top function. Now the derivative of the top function, remember y is going to be what we derive, x is going to be a constant. The derivative of x is 0, and so 0 minus 1 is going to be negative 1, since the derivative of y is negative 1. And then minus the top function, x minus y, times the derivative of the bottom function. Now the derivative of the bottom, since x is a constant, derivative of x is 0. Since y is the variable, derivative of y is 1, so 0 plus 1 is 1, all over the lower function squared. So once again, x plus y squared. And so when we simplify, we'll get negative x minus y if we distribute that negative 1 over, and then minus x plus y over x plus y squared. So negative x minus x is negative 2x. So we'll get negative 2x, and then negative y plus y will cancel, and so we get negative 2x over x plus y squared as the partial derivative of f with respect to y. So for number 4, we have w equals sine of alpha times cosine of beta. And so notice instead of x and y, we have alpha and beta, but they're going to be treated the same exact way. So let's go ahead and start by taking first the partial derivative of w with respect to alpha. So in this case, sine of alpha is going to be what we derive, and cosine of beta is going to be treated as a constant. So in this case, cosine of beta is just a constant, and the derivative of sine of alpha, remember, is just cosine of alpha. So this is going to be the partial derivative with respect to alpha. So now, taking the partial derivative of w with respect to beta, so beta is going to be the variable, and sine of alpha will be that constant. So we have sine of alpha times, now cosine of beta, the derivative is just simply times negative sine of beta, since the derivative of cosine is negative sine. So then we end up getting negative sine of alpha sine of beta. So now for number 5, we have w equals the natural log of x plus 2y plus 3z. So notice now we have 3 variables, x, y, and z, so we're going to have to take the partial derivative with respect to all 3 of them one at a time. So first, let's find the partial derivative of w with respect to x. And so remember, once again, the derivative of the natural log of some function u the derivative is going to be equal to u prime over u. So we're going to take the derivative of the inside function divided by the inside function. So in this case, x plus 2y plus 3z is that inside function. So when we take the derivative, remember x is going to be what we derive, and y and z are going to be treated as constants. So the derivative of x is simply just 1. Derivative of 2y is 0, and derivative of 3z is also 0, so 0 plus 0 obviously cancels. And so we get 1 over just the regular inside function, so 1 over x plus 2y plus 3z. So now let's take the partial derivative of w with respect to y. So in this case, the derivative of the inside function, now if x and z are treated as constants, the derivative of x is 0, and the derivative of 3z is also 0, and the derivative of 2y this time is simply just 2 over that inside function, once again x plus 2y plus 3z. And then finally, let's find the partial derivative of w with respect to z. So same exact process here. The derivative of the inside function, if z is the variable that we derive and x and y are constants, derivative of x is 0, derivative of 2y is 0, but the derivative of 3z is going to be 3 over inside function, once again x plus 2y plus 3z. That's the final answer. So for these next problems, let's go ahead and find the indicated partial derivatives. So for number 1, we have f of xy equals the square root of x squared plus y squared, and we're trying to find the derivative or the partial derivative of f with respect to x at the point 3, 4. So in this case, the partial derivative of f with respect to x is going to be equal to, well, I'm going to go ahead and change the square root of x squared plus y squared to look more like this. So x squared plus y squared to the 1/2 power, because now I can use the power rule. So remember, when we use the power rule here, or it's more like the chain rule, we're first going to take the derivative of the outside function. So that 1/2 is on the outside, so bring the power down. We keep the inside function the same, so x squared plus y squared, and then subtract the power by 1, so negative 1/2. And then we multiply by the derivative of the inside function. And so if x squared, or if x is going to be the variable that we derive, and y squared is treated as a constant, the derivative of y squared is simply 0, but the derivative of x squared is 2x. So we multiply by 2x. Notice the 2's will cancel. And so we get x over, I can bring that negative power to the denominator to make it positive. We get x squared plus y squared to the 1/2 power. So if that is equal to the derivative of f, or the partial derivative of f with respect to x, let's go ahead and evaluate it at 3, 4. So we're going to plug in 3 for x, and then 4 for y. So that is going to equal, well, we get 3 on the top over, well, 3 squared is 9, and then 4 squared is 16, so 9 plus 16 to the 1/2. 9 plus 16 is 25, and 25 to the 1/2, or 25, or the square root of 25, is 5, so we get 3/5 as the final answer. So now for number 2, we have f of x, y, z equals x over y plus z, and we're trying to find the indicated partial derivative of f with respect to z at the x value of 3, the y value of 2, and the z value of 1. So the partial derivative of f with respect to z is going to be equal to, now, x and y are going to be treated as constants. Z is going to be the actual variable that we derive. So if x is a constant, I can actually rewrite it. I can rewrite this function as x times y plus z. I'm going to bring that entire denominator up to the numerator and say y plus z to the negative first power, because now I can use the power rule. So we're going to take the derivative of the outside function, so bring that power down, so we get negative x. So leave the inside function like it is, so y plus z, subtract the power by 1, so negative 2 this time, and then multiply by the derivative of the inside function. So the derivative of y is obviously 0 because that's a constant, and the derivative of z is 1, so we just multiply by 1. So we're going to end up getting negative x over y plus 2 squared. So if we evaluate that derivative at 3, 2, 1, we'll get, well, negative x, so we get negative 3 on the top, over y plus z, so 2 plus 1 is 3 squared. So we basically get negative 3 over 9, which simplifies down to negative 1/3. So for this next problem, we have to use implicit differentiation to find the partial derivative of z with respect to x. So remember, in regular implicit differentiation, let's say we had x plus y equals y cubed. So in calculus 1, we would usually derive both sides. So we take dy dx of both sides. And so when we derive x, we would just derive it normally, so the derivative of x is 1. And then when we derived y, or every time we derived y, we would derive it and then multiply by y prime, or multiply by dy dx. So derivative of y is 1, and you multiply by dy dx. So that will equal, derivative of y cubed is 3y squared. And you'd also multiply by y prime, or dy dx. So the same thing works here. Since we are deriving z, or taking the partial derivative of z, every time we have to derive z, we have to multiply by the partial derivative of z with respect to x. And every time we derive x, we could just derive it normally. And so notice y is not in this notation, so we treat y as a constant. So let's say I go ahead and take the partial derivative of z with respect to x of both sides of the equation. So once again, every time we derive x, we'll derive it normally. Y is treated as a constant, and every time we derive z, we must multiply by this notation, derivative of z with respect to x. So derivative of x squared is always just 2x. Y squared is a constant, so derivative of y squared is 0. And then plus derivative of z squared. So once again, it's going to be 2z multiplied by the partial derivative of z with respect to x. And so that is going to equal the derivative of 3xyz. Now in this case, 3 and y are constants. So I'm going to sort of group them together and say 3, or in this case, I'm going to say 3yx times z. So notice there are two variables here that we need to derive, so we have to use the product rule. So obviously when we use the product rule, we're going to take the derivative of the first one. So the derivative of 3yx is simply just 3y times the second unchanged, times z, plus the derivative of the second. So derivative of z is 1, and then multiply by partial derivative of z with respect to x. So derivative of the second times the first unchanged. So multiplied by 3 times y times x. So when I simplify, I'll get 2x plus 2z times the partial derivative of z with respect to x equals 3yz plus 3yx multiplied by partial derivative of z with respect to x. Now, in order to find the partial derivative of z with respect to x, I must find a way to isolate that variable. So let's go ahead and, I'm going to go ahead and subtract 2x to the other side, and I'm also going to go ahead and subtract this term to the other side as well. So we get 2z times the partial derivative of z. Now when I subtract this term over, we'll get minus 3yx times the partial derivative of z equals 3yz minus that 2x term. So now what I can do with this is I can go ahead and factor out the partial derivative of z. So we'll get the partial derivative of z with respect to x times 2z minus 3yx. That will equal 3yz minus 2x. And then I can go ahead and divide over this term. So the partial derivative of z with respect to x is going to equal 3yz minus 2x over 2z minus 3xy, or 3yx. So that's the final answer. So for number 2, we have x minus z equals arctangent or inverse tangent of y times z. And this time, instead of finding the partial derivative of z with respect to x, we're going to find the partial derivative of z with respect to y. So let's go on and go ahead and derive both sides of the equation. I'll go ahead and take the partial derivative of z with respect to y. And so since x is not in this notation, x is going to be treated as a constant. Once again, whenever we derive z, we're going to have to multiply by this notation. And then y we can just derive normally. So derivative of x is a constant, so it's going to be 0, minus derivative of z, which is 1, times partial derivative of z over with respect to y. That's going to equal now arctangent, derivative of arctangent of y times z. Now the derivative of arctangent of some inside function u, remember, is going to be u prime so the derivative of the inside function, over 1 plus u squared. So if we go ahead and take the derivative of this inside function, now notice both of these we have to multiply, and both of these we have to derive as well, since only x is treated as a constant, so we have to use the product rule. So we're going to take the derivative of the first function, y, which is just simply 1, times the second unchanged, so times z, plus the derivative of the second. Derivative of z is 1 times the partial derivative of z with respect to y, times the first function unchanged, so times y, over, now we have 1 plus u squared, so 1 plus the inside function squared. So we can just write it as y squared z squared. And so when I simplify, on the left side of the equation, we'll get negative partial derivative of z with respect to y equals, now 1 times z is obviously z, and then plus y times the partial derivative of z with respect to y over 1 plus y squared is z squared. Now we need to go ahead and find a way to isolate partial derivative of z with respect to y, so I'm going to go ahead and multiply this to the other side. So we're going to end up getting, now I'm not going to distribute the partial derivative, so we'll get the partial derivative of z with respect to y times 1 plus y squared z squared, and that's going to equal z plus y times the partial derivative of z with respect to y. Now the next thing I'm going to do is subtract this term over to the left side. So we're going to end up getting negative partial derivative of z with respect to y times 1 plus y squared z squared, and then minus that term that I need to subtract, so minus y times the partial derivative of z, and that's going to equal z. So now I'm going to go ahead and factor a negative out from both of these terms. So we get a negative partial derivative of z with respect to y. So we get here 1 plus y squared z squared. Since I factor out a minus, it's going to end up being a plus, so we get plus y. And that's going to equal z. So now I can go ahead and divide over this term, or these group of terms here. So we get negative partial derivative of z with respect to y equals z over 1 plus y squared z squared plus y. And then if I go ahead and divide over the negative, we'll get the partial derivative of z with respect to y equals negative z over 1 plus y squared z squared plus y. So now the next section is going to be about higher order derivatives. So obviously in Calculus 1 we might have had something like y equals x cubed. So then the first derivative, y prime, would obviously be 3x squared. The second derivative would be 6x. The third derivative would be 6. The fourth derivative would then be 0, and you can go on forever, but you'll keep on getting 0. Now, there's a similar process in partial derivatives as well, where if you have, let's say, the multivariable function f of xy, obviously we just looked at how to take the partial derivative of f with respect to x. We can just write it as f sub x, and if we take the partial derivative with respect to y, we can write it as f sub y. So now the second derivative, we could also write it as f of sub x and then y, or we can also write it as f sub x and then x. And for f sub y, it works the same way. You can either have f sub y x or f sub y and then y. So if we look at f sub x x, this tells us that the first derivative we're going to take, the first partial derivative is going to be with respect to x, and the second one is also going to be with respect to x. For f of x, f sub xy, the first one is going to be x, and then the next derivative we take, or the next partial one, is going to be with respect to y. And then the same thing works for the other two. Now, Clairaut's theorem states that, let's say you're taking the partial derivative of f with respect to x, and then with respect to y, of the same function, and then you're taking the partial derivative of y, and then the next one with respect to x, of the same exact function. Now, Clairaut's theorem says these will give you the exact same result, or the exact same answer, as long as the function is continuous. If it's not continuous, then it may not give the same answer, but if it's continuous, then you are guaranteed the same answer. So in this case, whether it's xy or yx, the order does not matter. as long as, once again, it's continuous, the function. So for number 1, let's verify that the conclusion of Clairaut's theorem holds, that is, u sub xy equals u sub yx. So once again, the order does not matter as long as the function is continuous. So for number 1, we have u equals x sine of x plus 2y. So let's go ahead and first find u sub x, or in other words, the partial derivative of u with respect to x. So once again, x is going to be the variable that we derive, y is going to be a constant. So notice we have two separate functions here, so we have to use the product rule. So we take the derivative of the first function, so derivative of x is 1, times the second function unchanged, the sine of x plus 2y, plus the derivative of the second function. Now, the derivative of sine of some function u is obviously going to equal cosine of u times u prime. So it's going to be cosine of x plus 2y, we leave the inside unchanged, multiplied by the derivative of the inside, and the derivative of x plus 2y, if y is a constant, it's going to be 1 plus 0, or simply just 1, multiplied by the derivative of the first function unchanged, so times x. So we're going to end up getting sine of x plus 2y plus x times cosine of x plus 2y. So now, given that we have u sub x, now let's find u sub xy. So we're going to take u sub x and then now partially derive it, or partially derive u with respect to y now. So in this case, y is going to be the variable that we derive, and x is going to be a constant. So derivative of sine of u, remember, is cosine of u, so cosine of the inside function left unchanged, times the derivative of the inside function. So if x is just a constant, derivative of x is 0, so we get 0 plus 2, which is 2. And then we have plus, well in this case x is a constant, and then derivative of cosine of u, once again, is equal to negative sine of u times u prime. So we have x times negative sine of the inside function left unchanged, and then times u prime. So the derivative of that inside function, x plus 2y, is once again going to be 0 plus 2, which is 2. So we're going to end up getting cosine, or 2 times cosine, of x plus 2y plus negative 2x sine of x plus 2y. And so if I want to, I can go ahead and get rid of that plus. So we get 2 cosine of x plus 2y minus 2x sine of x plus 2y. So now, given that we already found u sub xy, now let's find u sub yx and verify that we get the exact same result. So first, finding u sub y, we're going to derive y and keep x as a constant. So in this case, x is a constant once again, so we have x times now the derivative of sine is cosine of the inside function times the derivative of the inside function. So if we're deriving y, once again it's just going to be 0 plus 2, which is 2. So u sub y is going to equal 2x cosine of x plus 2y. And so now we're going to find u sub yx. So the second derivative now we're going to derive with respect to x. So notice there are two separate functions here. These are two separate places where there are x's. So we're going to have to use the product rule. So in this case, we're going to take the derivative of the first function, which is 2, times the second unchanged, plus the derivative of the second function. Derivative of cosine is a negative sine of x plus 2y, times the derivative of the inside function. So that's obviously just going to be 1 plus 0, which is 1, times the second function unchanged. So u sub yx is going to equal 2 times cosine of x plus 2y minus 2x sine of x plus 2y. And so notice u sub xy and u sub yx yield the same exact answer. So now for number 1, we have f of xy equals 3xy to the fourth plus x cubed y squared. And we're trying to find the indicated partial derivative of f sub xx and y. So let's go ahead and first find the derivative of f, or the partial derivative of f with respect to x. So that is going to be, well, x is going to be the derivative, or the variable that we derive, and y is going to be treated as a constant. So the partial derivative with respect to x of 3x times y to the fourth. If y to the fourth is a constant, we have 3y to the fourth as the derivative, or as the partial derivative. And then plus, now y squared is again a constant, so the partial derivative is going to be 3x squared and then y squared. So now f of f sub x, x. So now we're going to derive once again with respect to x of what we have for f sub x. Since y is a constant, derivative of 3y to the fourth is 0, and then plus the partial derivative of 3x squared y squared. Once again, y squared is a constant, and the derivative at 3x squared is going to be 6x. So we have 6x to the first times y squared. So that is going to be equal to f sub xx. So now let's find f sub xxy. So now we're going to take the partial derivative of f with respect to y. So once again, y is going to be the one that we derive, x is going to be a constant. So the derivative of y squared is simply just 2y. So we get 6x times 2y to the first. So that will give us a value of 12xy.